our recap. Buang masa sebanyak 15 minit. Okay, so at this point, we should already know about KE, UG, and US, the difference between these three energies and what is the equation. Okay, so KE, the equation for energy is 1 over 2 mv squared, and this guy UG is mgh, and this is specifically related to vertical distance. Vertical distance sahaja. So if you have a distance like this, MGH will not apply. MGH is only related to vertical distance. Either you are going up or you are going down. Only vertical, only in the y-axis. Y-axis yang original lah, tak adalah yang parallel, incline ke apa ke, our y-axis. So it is related to height, up and down, and only related to vertical distance. So this is very important to take note of. And then we have US, which is the spring potential energy. Sometimes we call it as elastic potential energy. For this equation, where US is equal to 1 over 2 kx squared, this is specifically for a spring. This is specifically for a spring. And we call it as elastic potential energy. There are other instances where we have elastic potential energy. For example, benda yang boleh stretch out macam getah ke apa, that would have potential energy as well. However, this equation only deals with spring systems only spring systems, and this is what is covered in this syllabus. So only use this equation for spring. Kalau elastic benda lain, kena cari equation lain. Okay, and then we know that at this point we should already know that when we have a change in KE, let me use a different color. When we have a change in KE, we would have work. Ataupun work is related to the change in energy. The same goes to this guy, the change in UG, work. The change in potential energy ataupun the change in elastic potential energy or spring potential energy. Now, sometimes they just write these two guys as U. So sometimes they say EI equals to EF, whereby EI is KE plus U. This is initial, KE final plus U final. And you should know that this is UG and US, depending on what system you're talking about. This U is the generalized form for both of these guys. So if you have all three together in one system, where's my slide? When you have all three in one system, so you write that as KEI, UGI, and USI. Okay, and then equals to KE final plus UG final and U spring final. So if you have all three in one system. So that U, jangan confuse kalau diorang letak U sahaja, it means for both. Pick one ataupun use both depending on the system. Okay, so that is your conservation of energy. Sometimes we have non-conservative forces and sometimes we have conservative forces. So let's talk about that. So we have two types of forces, conservative and also non-conservative. And I told you the easiest way to remember what is non-conservative is it is something that makes our system lose energy. For example, friction, air resistance, ataupun air drag. So these are the things that cause our system to lose energy. So we can lose energy, right? We can lose energy. In general, we can always lose energy and we regain it as something else. For example, we have an incline. I start from this, bukan saya lah, let's say Balkis. Tadi Balkis jadi kita punya host. So this is Balkis on a sled. So Balkis, initially she had a MGH of, who knows, maybe this height is 10 meter. And then Balkis campur dengan sled is 50 kilogram. 9.81 and H is 10. But when Balkis goes down over here where H is equal to 0, this is H equal to 0, this is, let me write it here, H equals to 10, H equals to 0. So when Balkis goes down, here her UG is now mg0. So that energy becomes 0, but where does it go? It is lost as mgh, it is lost as gravitational potential energy, but we need to gain it somewhere else. And when Balkis goes down the incline, she also speeds up. So actually, your mgh is being transformed into ke. Okay. When Balkis is halfway through sliding down, where H is equal to 5, her energy is now both Ke and Ug. But when she reaches the final point where her Ug becomes a 0, all her energy is now only Ke. So here you can see that the initial energy that we started with, whereby our Ke was equal to a 0 because she was not moving. Ke was 0, Ug was mgh, 50 times 9.81 times 10. Halfway through, the energy that she initially had was converted into Ug and Ke. Ataupun she lost Ug and some of that energy became Ke because she is gaining speed. And when she reaches the bottom of this incline, her mgh becomes 0. So she totally lost Ug, but that energy went to become Ke. So energy is not lost. Energy is transformed from Ug, ataupun energy is transformed from gravitational potential energy to become kinetic energy. So this is what happens when we are talking about conservative forces. Okay, why? Because we are talking about Fg, gravitational force. So gravitational force is a conservative force. Maksud kat sini is when we lose it, it becomes something else. We can recover it as something else. It becomes kinetic energy. mgh becomes kinetic energy, or kinetic energy becomes mgh. But for non-conservative force, if you lose it, once you lose this energy, you cannot recover it. It's gone. Once you lose it, you cannot recover it. Okay, so if it's not recoverable, what does it become? It becomes heat, vibration, it can become sound, all those things that you can't put back into the system. mgh to Ke, you can flip it around. You can transform it from Ke to mg, mgh to Ke, so on. But for non-conservative force, if you lose it, it's gone. It is gone into the environment. So if Balkis punya sled is not smooth, therefore she would have friction. So her EI, this is our EI, initial energy, would be reduced by the work done by this non-conservative force. Therefore, her Ke will also reduce because we started with a lower EI. We started with a lower, we started with a lower EI. Therefore, our EF will also be lower. Okay. Minus non-conservative work done. So akan berkurang lah sebab kita punya energy ditolak oleh work done by friction. So we are losing energy. And again, if we are using this equation but you don't like your non-conservative force, work done by non-conservative force in the initial side, you can put it on the other side, but it becomes EF plus W and C. So if it's in the initial side, it is a negative. If it is on the final side, it should be a positive. So please take note on this. Do not put both sides negative. Tak, So initial je negative, dekat final dia akan jadi positive. Okay, so this is the difference between conservative force. You can recover it back in form of other energy. Non-conservative force, you totally lose it into the environment. And non-conservative forces are friction and air drag in the form of heat, vibration, and sound, so on. Okay, so that is conservative forces and non-conservative. So saya tak habis lagi cerita pasal KE sebenarnya. So there's another thing that we forgot about kinetic energy, which is the kinetic energy, which is the work energy theorem. Work energy theorem. What does the work energy theorem tells us? It tells us that the net work on a system ataupun the total work done on a system or the net work on a system is equal to the change in its kinetic energy. To use this theorem, you need to have only the speed that is changing. For example, let me get rid of this first. For example, oh, why did I do that? Yeah, let me put it somewhere else. Kita nak cakap pasal this is conservative force. Hey, hello, where did it go? Is it here? Okay. Okay, so let's go for an example for work energy theorem. Okay, so I have a box and I'm pulling this box by a pulling force, and this box is traveling to the right by a distance or a displacement of 5 meter, let's say, and this guy is 100 Newton. So this is our final destination ataupun final displacement lah of this box. So this box is on the ground. There is force, there is displacement, so we know that there is work done. And this box started with a u. I should write this as a small u because this is velocity. Small u of 15 meter per second. And there is some velocity at the end that we don't know yet. So in this situation where we have force and we also have displacement, so we know that we have work done, and we also have a change in our velocity, so we can use the work energy theorem to find that final velocity. So W net, the net work done, assuming that this is the only force that we're considering, benda lain macam tak adalah, kita anggap invisible dulu. So assuming that this is the only force acting, so we have a W net of force pulling of 100 times with 5. So we would get 500 joules. And this would be 1 over 2 mv final squared minus 1 over 2 mv initial squared. We know what our mass is, supposedly, and we know what our initial velocity is. So 1 over 2, let's say the mass of this box is 2 kilogram. So I would say this is 2, and this is V final minus 1 over 2. This is 2, and V initial, which is 15. Macam tu. So cancel out, 15 squared, 500 minus 15, 500 plus 15 squared, to square root kan, you will get your VF. So this is the instance, ataupun this is the scenario where you can use the work energy theorem. You know what is the net work done here. By net work, I mean the net force. You need to know what is the net force, and then times it with displacement. And then when you know what is the work done, you can equate it to your kinetic energy equation. This is when it is only related to velocity change. There's another thing that we need to talk about, which is what if we have several forces acting on a system? So when I talk about W net, what does it mean? So W net is equal to F net that is parallel to displacement. I'm going to repeat myself here. When I talk about work done, net work done, ataupun total work done, I am talking about F net that is parallel to our displacement. So if I have a box and I have like all these forces, FP, and I have this is FP juga lah kot. This is pull, this is push. And what else? I have friction going this way because my motion is this way. This is my X. So I want to know what is the net work done. So the way that I can find out what is the net work done is, first method is finding all work done. Finding all the work done for each force. For each force. This is one approach of doing it. Another approach that you can do is finding the F net that is parallel to your X. You would get the same answer for these two guys. Dua-dua approach adalah betul. Tapi yang approach yang paling simplified is this guy lah. Finding the net force and then baru darab dengan displacement. This one is correct but slightly panjang. So how do we know what is the F net? I need to know what is acting in my x-axis. So therefore I need to resolve. This becomes F push cosine whatever theta that is, and ke bawah ni adalah F push sine theta, and then in my axis here that is parallel to my displacement, my F net in the x direction is F pull plus F push cosine theta minus friction. So this is my F net. This is my F net. Dan lepas dah tahu magnitude ni, baru darab dengan displacement, you will get your W total. This is the approach to finding F net. Kita dah belajar ni, semua kita dah belajar. Saya recap balik je. This is from chapter 3. Okay, what else do I need to tell you about work energy theorem? So work energy theorem ni, when we are talking about work energy theorem, we are also assuming a constant force. Constant force acting. We are not talking about a variable force. Remember I told you we have constant force and also variable force. So for work energy theorem, we are assuming that we have a constant force. Therefore, our A is also constant. Daripada situ kita boleh cari kita punya, kita boleh pakai inilah, kita boleh pakai the work energy theorem. We are assuming a constant force when we are using work energy theorem. When we have positive work done, it means that my V is going to be greater than U, and when I have negative work done, my V is going to be less than U. Dia akan slow down. This one, if I have positive work, I will be speeding up ataupun I will be gaining energy in the form of KE. Any other questions about what we have learned so far? Ada lagi tak? And then I'm going to talk about spring. So any questions about MGH and KE? And then the work energy theorem. Okay. So everyone's okay. I know it's a lot of stuff because we're tying chapter 2, chapter 3, chapter 4 together. But you guys can do it. So slow. Okay, so KE, UG, US, spring. Okay, now we're talking about spring now. Next slide. So spring potential energy. So the spring potential energy comes from Fs, where Fs is equal to minus Kx. What is K? K is the spring constant. And this is the displacement ataupun the stretching or the compression of the spring. Compression. Okay, when you have compression, we're going to assume that it is a negative X. And when you are stretching it, we are going to assume that it is a positive X. Okay, so when I am talking about the potential energy of a spring, I will label this as PES ataupun US is equal to 1 over 2 KX squared. And then when I'm talking about stretching and compression, I need to define what is my equilibrium position. So this is a new term, equilibrium position of a spring. I haven't told you guys about this one. So when our spring is not being stretched or being compressed, it is at equilibrium. and I would label the end point of this spring as my equilibrium point, or x equals to 0. Equilibrium point. Equilibrium point. Okay, so when I am stretching this spring, what I'm doing is I am shifting this x ataupun this end of the spring to some distance. I'm shifting it because now my x is over here. My end of the spring is at a different position and the position is to the right. I am defining to the right as positive x. When I'm stretching it, I have a displacement of something that is a positive x. Let's say it is equal to 5 centimeter, contoh. And when I am compressing it, with respect to its equilibrium position, I am having a displacement. This spring has a displacement of minus x equals to 2 centimeter, contoh. So this is 0. To the right is a positive. To the left is a negative. When they talk about equilibrium position, it means the point where the spring is not being stretched or being compressed, and commonly we label it as the end of the spring to be the equilibrium position ataupun equilibrium point. We label this as x equals to 0. Why is it important to label this? Sebab kita nak tahu direction kita punya force nanti. Okay, so let's say I have an extension of the spring by 5 centimeter. I want to know what is Fs. So I can say, let's say our K for this guy is yang senang, 20 Newton per meter. That is your spring constant. So Fs for this spring, let me write it here. Kenapa nak jauh-jauh? Fs for this spring is K minus Kx, so minus 20. And X is, we are stretching our spring, so 5 centimeters, so it becomes 0.05. Bagi 100 kan? Okay, 0.05 meter. This is Newton per meter, so meter with meter cancel out. So I'm left with Newton. So your answer will be 20 times 20 times 0.05, you would get minus 1 Newton. Betul tak? Ada orang kirakan tak? Betul ke salah? Dapat 1?
Betul.
Okay. So I got minus 1 Newton. So this sign immediately tells me, okay, so it's a minus. Which way did I define to be my positive? So my positive was to the right. If my force that I got from this equation is a negative, it means that my Fs is this way. Oh, sorry, kita nak stretch kan? My Fs is acting this way. Fs is going to the left. How did I know this? Because I defined to the right as positive and to the left as negative. My answer is negative. I know it's to the left. This is why it's important to define your equilibrium position and defining your positive and negative for a spring system. Okay, so this is for Fs. I also mentioned to you that Fs is equal to the minus of F applied. What is F applied? F applied is when I, a human, when I am stretching the spring, I'm applying a force on the spring. So it is equal but in opposite direction. So if Fs is to the left, F applied is to the right sebab dia akan terbalik dengan Fs. So if Fs is minus 1, this guy will be minus 1, which is 1 Newton. Positive force tells me that it is to the right. So F applied is to the right. Okay, so this is about your direction lah. Conventions of your direction. Sekejap apa lagi saya nak cerita? I think work energy theorem saya dah cerita habis. EI equals to EF with WNC pun dah. So all of this energy is in joules ataupun in Newton meter, and they are all scalar quantity. KE is a scalar quantity with joules, UG is a scalar quantity with joules, US is a scalar quantity with joules, delta KE, delta UG, delta semua tu semua scalar. WNC is a scalar quantity. It's a work done. Work is a scalar quantity. The only thing that's not a scalar quantity is the forces that we're talking about. Non-conservative and conservative forces are both vectors. So itu saja vektor dalam cerita chapter 4 ni. Okay? Alright, so let's start with our example. Kalau tak ada soalan, I'm going to start with our example. Kita dah buat example ni. I'm going to skip this one. We have done this one as well. Oh, okay, I haven't talked about this one. Saya ada soalan saya ada banyak terima soalan about why do I have this cosine 180 in my equation? Let's say, I think we need to do an example first before I can tell about this one. Okay, kita buat example dululah. Okay, so a skier traveling 12 meter per second reaches a foot of an 18 incline and glides 12.2 steadily up. So dia ada incline. Dia dekat foot. Foot ni maksudnya kat ujung ni lah. So this is the skier. I don't know how to draw a skier. Anggap ni skier lah. So this guy is moving up the incline steadily before coming to a rest. Okay, before coming to a rest, which means that it started with U of 12 meter per second. It glides up and then it came to a rest. So V equals to 0. The incline is 18 degrees. And what else? We need to know what is our average coefficient for friction. Okay, so we need to know what is mu. Okay, perkataan average ni boleh abaikan lah. It just means that for the coefficient of the surface lah. Okay, we are always finding the average, so don't worry about that. So U is 12 meter per second, V is 0 because it came to a rest. Mu is what we're trying to find. Okay, so how do we do this problem? So we know that we need to use the conservation of energy for this guy. So we have EI equals to EF. We know that we have friction, so there is going to be a non-conservative work done. So this equation, we have to rewrite it to become W and C equals to EF. So what are the energy that is involved here? When this guy is climbing up steadily, it is actually gaining potential energy. So we know that we are talking about KE and also UG. Do we have US here?
No.
Okay, tak ada. Tak ada. And then we have KE final. Dia come to a rest, so V final adalah kosong So let's write this. 1/2 MVI squared minus with WNC ataupun friction times displacement equals to, oops, I missed one, plus MGHI plus, sorry, it should be a minus, WNC equals to 1/2 MV final squared plus with MGH final and tak ada dah, okay tu je. So the first thing that we need to know when we're talking about potential energy is defining what is our reference point. This is our reference point. We are going to say this is H equals to 0. This is H equals to 0. And then when it glides up, it will reach a point. Oh, dia dah bagi tahu 12.2. So dia glides up by 12.2 up here. So we need to know what is our height over here. So use your sign Sine of 18 equals to opposite over hypotenuse. Opposite is the height and hypotenuse is 12.2. So you can solve for height, you would get sine of 18 times with 12.2 dapat 3.77. Okay, so this is what we got for our height, 3.77 meter. So when I am at my final point, my H is at 3.77. Okay, so what else? Our U at this point is 12. Our V at this point is 0. So actually we can put in the values now. 1 over 2, we don't know what is the mass, M. UVI is 12 squared. And then M is... Mana tak bagi tahu mass eh? Oops. Haikal pula jadi pin ni. Pin my video. Okay, continuing. So M 9.81 and H is 0 for our initial condition because this is our reference point. Okay, and then minus with W and C, which I don't know yet. And then this is equal to 1 over 2 M. V final is 0. So Y, that is a 0. Saya suka bila benda jadi kosong. And then M 9.81 and then we have our final height as 3.77. Let me make this smaller. If you have any questions, please interrupt me. Please interrupt. Do not wait sampai lupa. Lepas tu tak tanya. Please interrupt me. It will help your friends as well. Okay, so that is your equation. Boleh cari M terus ke doktor? Boleh cari M terus ke doktor? Guna equation yang... Yes, Haikal, what is it? S equals to 1 over 2 macam tu.
Yang kan ada formula yang nombor 2 tu kan. S equal to 1 over 2 U plus V T. S kita dah ada, U, V kita dah ada, T je tak tahu. Tapi kita dah ada kan.
Tapi kita nak cari T ke?
Yalah, lepas tu masukkan tu je dapatlah mass kan. Sebab meter per second. Tak boleh.
Kejap. Meter
faham
per
tak?
second. Nak cari mass.
Nanti kan dapat T. Lepas tu kan ada 12 meter per second kan. So S M 12 equal to M per S. Naik atas. Boleh dapat M kan? Ke tak boleh?
M tu mass ke meter?
Mass. Kan? Mass per...
Ini meter tapi. Macam mana nak dapat M?
Sekejap. Okay. Maafkan saya.
Okay. Okay, let's continue. Thanks, Haikal. Yang ni meter per second bukan mass per second. Okay. Haikal jangan dia bore kesian dia. Okay. So 1 over 2 M, VI is 12 squared. Tak apa, saya appreciate any kind of discussion. It's okay, we are here to learn. Minus WNC and plus MGH. So M kita tak tahu, kita nak cari average coefficient of friction. So friction punya equation is mu R. And if I were to draw the free body diagram for this guy, it would be mg. And Allah, kenapa macam susah tulis ni? Saya tadi nak bayangkan pula. Okay, so this is, kita bayangkan kotak lah sebab itu yang menyenangkan hidup saya. mg, and this is our incline like this. Okay, 18. So this would become mg cosine 18. And this would become mg sine 18. Macam tu. So since our box is not flying, I can say that Fy equals to 0. Oops, silap tulis. Let me write this properly lah. Nanti kan korang confused. Sekejap. Ni saya lukis orang skier tu jadi kotak sebab saya pening kepala tengok gambar saya sendiri. So 18. So this is mg cosine theta. This is mg sine theta. This is reaction force. And then we also have friction. So I want to know what is my reaction force because I want to know what is my friction. So we know that this box is not flying, it's just moving on the incline. So we can say that our net, net in the Fy is equal to 0. And what is in our Fy? It is R minus mg cosine theta. This is equal to 0. Therefore, our R is mg cosine 18. Okay, so now I can put this in here. So now it becomes, whoops. So now it becomes minus mg cosine. Tak cukup tempat lagi. Give me a minute. Kenapa tak boleh ni? Sekejap. Buka ini semua. Delete. Dah jadi group. Oh yes, I did group it just now. Ungroup. Okay, let's continue. Alright, so kita akan substitute the value for W and C. What is W and C? W and C is friction times with our displacement. Friction is this way. Friction is this way. Kita tengok sini sekejap. This is our friction, yang pink ni. And this is our displacement, S. So S and F, S is this way and friction is this way. To find the work done, we need to know what is the angle between them, which is 180, because they are opposite direction. Okay, I'm going to repeat myself here. Work done is the dot product of force times displacement. Dot product. So when you expand a dot product, you need to know what is the angle between F and S. So F cosine theta and S. So we need to know what is the angle between the F and S. So friction is this way and our displacement is the other way. So the angle between them is 180. Therefore, if I were to write my equation for W and C, let me write it somewhere. W and C, this would be friction cosine 180 times with S. In this case, our S is 12.2. This is the motion, and this is where friction is parallel to the motion. Friction is this way, motion is this way, ataupun S. So this is why it is 180 because it is in the opposite direction. If I have friction in the same direction as my displacement, then the angle between them would be 0. Okay, so I hope this is clear for everyone. Friction terbalik dengan displacement. The angle between them is 180. Therefore, my work done equation is force dot product with S ataupun F cosine theta S. F in this case is, apa tadi? Sudah kira ke belum? F is mu R and cosine 180 is because they are opposite direction. What if friction is in the same direction? They would look like this. Kalau F dengan S sama direction, this is F and this is S, tak ada angle. Tak ada angle between F and S. Kosong. Kalau ada angle, bagi tahu lah angle berapa. Kalau angle macam ni, separuh bulatan. So it is 180. If they are together on the same axis, same direction, there is no angle between these two vectors. Kosong. But now that they are not, So the angle between them is a cosine and cosine 180, which gives me -1. I need more space. Let me duplicate this. Okay. What should I buang? This one. And then kita akan letak benda ayah ni kat situ. So that I have more space. No, not really. Dan kita adjust ni dekat ke sana. Okay. So again, work done is friction times the motion. Friction is this way. Motion is the other way. So when you have two opposite vectors, you would have a work done that is negative ataupun a work done with an angle of cosine 180. Okay, so ada Syeki tanya, doktor boleh tak kalau kita terus letak minus without the cosine 180? Yes, you can. Provided that you understand that it is a negative. Kalau tak pandai nak pakai positif negatif, jangan pakai, jangan terus letak, pakai angle. Boleh kalau faham? Kalau opposite vectors tak kira exist macam mana pun, dia akan negative work done. For example, if my force is this way and my displacement is this way, I know that I would have negative work done. Kenapa? Angle between them is 180. S macam ni, F macam ni, 180 minus work done. Apa lagi yang pelik-pelik? Macam ni S and this is F, sama macam yang kita tengok tadi. 180 work done is negative. If you don't want to use the angle, you can immediately put in the negative sign, no problem. Boleh You just have to know same direction positive work done, opposite direction negative work done. So mg cosine 18. So this is for R. Friction is mu R. Mu is unknown. So this is mu mg cosine 18. Kita nak cari WNC tadi. WNC is friction cosine 180. And then times with S. And friction is this guy. Mu mg cosine 18. Cosine 180 is -1 times with S, which is 12.2. Okay, so far everyone following me? Ada tak part yang confused? So far everyone okay?
Okay, doctor.
Okay, so that's good. Any questions so far? Tak ada Okay, kalau ada boleh tanya So I am solving for the values and keeping whatever yang unknown ni at one side. So 9.81 darab dengan cosine 9.81 from G times with cosine 18 times with -1 times with 12.2. So you would get minus 113.82. Okay, so that is a negative work done. So now we can put it into our equation over here. Minus mu m113.82. So now I can do the most favorite thing in the world, which is cancel out my m's. So now I don't have to solve for m. Okay, so now I'm left with this guy, mu 113.82, a minus, left with this and this. So sepatutnya boleh solve lah. So mu akan dapat blah blah blah, tak tahu. So let's see what's the answer. Sama tak kita punya jalan kira? Kosong tambah dengan 1/2 mu squared equals to mgh plus 0. Kat sini dia letak dekat final side. Tadi saya letak dekat initial side, so it became a negative. So 0 plus 1/2 mvi squared plus, minus WNC. So this is what we did just now. And then mgh plus 0. This is from the KE and this is from the UG. Kita start daripada bawah. Bila kita naik, kita stop, KE jadi kosong, UG ada value. So kat sini dia cakap kita punya mu R. Oh, dia tak letak R lagi. So I would say it's the same lah. It's the same approach, cuma slightly different in terms of dia letak WNC dia dekat final site, but the rest is the same. We have this guy. Kita kira lah, kita kira. Let's see if we get the same answer. So 12 squared divided by 2. 12 squared divided by 2. And then I'm going to shift this guy over here sebab saya nak jadikan dia positif. So 12 squared divided by 2 minus with 9.81 times 3.77. So I've got 35 and then divide by 113.82. So I get 0.31 sama. 0.31. Tak ada unit. Coefficient of friction, no units. Okay, so this is how you do it. Any questions about this one? So let's do a recap on what we did. First of all, I said EI is equal to EF, but we have friction, so we need to include the WNC over here. If your WNC is on your initial side, it needs to have your negative sign. If it is placed on your final side, it needs to have the positive sign. Tak kisah mana-mana. What is WNC? WNC is force of friction times with displacement. Most of the time, students will make a mistake and just put the force of friction as WNC. That is wrong. Work done is always force times displacement. We need to multiply it with the displacement. So, okay, so what is EI? EI we started with at the bottom of our incline, H is equal to 0. So we know that our MGH is 0. So this is what we did. MGH is 0. We started with some initial velocity. So we have value over here and we have value over here. This is equal to the final energy. Our final velocity is 0, so our KE is 0, and we have some MGH value. So just solve macam biasalah. The tricky part was over here, finding the work done for non-conservative force. Okay, so I hope everyone is clear. Ada soalan tak? Okay, Adam tanya, doktor kalau letak WNC kat sebelah final tu ada negatif tak doktor? Kan dapat WNC as minus. It becomes a positive. It becomes a positive work done. Kita solve dapat negatif kan? When you put it at the final side, it becomes a positive. So kita tengok kat sini ya. Where is it? Ada tak diletak kat sini? Kat answer. Saya tak suka tengok solution sebab saya tahu tak faham solution buat apa. Kejap. Let me see this guy. Okay, dia letak dekat final side kan? Tengok kat sini. This is initial and this is final. So dia put, this is mu R times S. This is our WNC. Kat sini you can see that they put a positive sign. Walaupun kita solve tadi, kita dapat negatif. You have to make it positive. Negatif ni untuk initial side sahaja. Okay, so I hope that is clear. It's a little bit confusing. Just keep it on the initial side if you like. You don't have to change.
Doktor,
Yes.
Saya tak faham yang WNC tu.
Tak faham WNC. Okay, let's go back to WNC.
WNC tu kan sama dengan friction dengan S kan? Displacement. Lepas tu, macam mana tiba-tiba ada cos 180 tu?
Oh, okay. Okay, let me talk about that one. Okay, new slide. Okay, so tadi we talked about WNC. Okay, WNC is friction times with displacement. Okay. The equation for work done, is force dot with displacement. This is where this equation came from. Ni kita punya base equation. For work done NC, non-conservative force. The force here is our friction. Kenapa saya macam ni? The force here is our friction and the displacement here is our displacement jugalah. So this is where we got our equation. So when I expand this equation, this basic equation, it becomes F cosine theta S. Remember, where theta is the angle between two vectors. What are those vectors? Force and displacement. So if I have force like this is the angle. This is F, this is S. If I have force like this is the angle. Tak kisah macam mana, asalkan ada angle between the two vectors. Now in this case, our force and our displacement was this way. F macam ni, S macam ni. What is the angle between them? It is 180. So I put that into my equation. So this becomes friction force ataupun small f. Let's just make it a small f. Cosine. What is the angle between them? 180. What is the displacement? S. So this is where the cosine 180 comes from. If your friction is not parallel to your displacement, let's say your friction is this way, which is impossible lah sebenarnya. Friction is always parallel to displacement. Ada tak instances lain? Non-conservative force. Okay, let's say we're talking about air drag lah. Our motion, tak boleh juga. So it will always be a parallel sebenarnya for non-conservative force sebab dia opposing motion. So where does the cosine 180 comes from? It is from the angle between the force and also the displacement. If you don't like this approach, it makes you confused. You can just say the work done by two vectors that are in opposite direction is negative. Macam yang Shiki cakap tadi. Okay, work done by two opposite vectors is negative. And work done by vectors that are in the same direction is positive. Faham ke kenapa cosine 180? Cosine 180 will give us -1. Work done by two opposite vector is negative. Sama this is -1. Does that make sense? Ke lagi confused? Okay, so what if our force is in the same direction as displacement? So F macam ni, S macam ni. What is the angle between them? The angle between them is 0. So how does my equation look like? So W equals to, let me write it, W equals to F dot with S. Expanding this equation, F cosine theta S. Theta is the angle between them. F cosine 0 S. This would give me +1, which is just Fs. Yang ni W equals to -Fs. Boleh je nak terus letak negatif tu. Tak nak letak cosine 180 pun boleh. Asalkan faham. Opposite negative sama direction positive work done. Faham ke? Dah okey ke? Tak okey. Ke nak repeat
Faham.
lagi? Faham
Thank you, Doctor.
Welcome. Okay, let's take a 5-minute break. Then we will continue with more examples. 3:15 p.m. Go get your water, toilet, whatever. Come back at 3:15. Kalau soalan boleh tanya. Okay, so Adam tanya kalau angle dia kosong, WNC becomes positive. Kalau letak sebelah initial jadi negatif juga ke? Okay, tadi saya cakap pasal work done Okay, let me jawab soalan Adam dulu So tadi saya cakap pasal work done. I didn't talk about work by non-conservative force. So non-conservative force dia memang akan lose energy from the system. So it will always be negative in the initial side. Tak ada instance yang dia jadi positif dekat initial site. So even ni contoh untuk work done yang biasa, yang force bukan friction. But when we're talking about friction, it will always be opposing motion. Friction is always opposing motion. Remember guys, friction punya condition is to oppose motion. So work done is always negative. And when you have work done that is negative, this is going to be negative in your initial energy punya side. And it will become positive WNC in your final side. Pick either one. Okay, so doktor, okay, Husniah tanya, doktor tadi doktor tulis cosine 18, cosine 180 is -1. Kenapa doktor tulis macam tu? Mana Yang ni ke?
Bukan dekat slide sebelum ni.
Oh, okay, sekejap.
Yang tu, yang WNC tu. Dekat situ.
WNC. Yang ni cosine 18 ni referring to free body diagram. Kejap, free body diagram pun macam tak betul kan. Patutnya saya lukis elok-elok. Okay, kita tulis. So free body diagram, anggaplah kotak ni skia tu Saya tak boleh nak lukis orang tu. So mg, this is going to be your 18 degrees. Betul kan? This is going to be your 18 degrees. This is mg cosine theta. Is it mg sin theta? Saya tersilap Kejap. Angle that is touching. Kenapa saya letak cosine Cosine. It should be sine Did I make a mistake? Saya pun confused. Okay, so this is 18 degrees. Sekejap. 18. Macam tu. Betul lah kat sini. mg cosine. So saya silap. So it should be a sine. How did I get the answer? That's amazing. Okay. So this is mg cosine theta. Oh betul lah. Saya nak cari R. Sorry. So this is mg sin theta. So R saya nak cari R kan. Mu R is friction. R is mg cosine theta. R is mg cosine theta. Mu R, so mu mg cosine 18. This is 18. Okay, mu mg cosine 18 and then -1 refers to the cosine 180. Ni dua benda yang berbeza. Cosine 18 ni datang daripada equation kita yang kita cari yang ni. So this is 18. Let me put it here supaya korang tak confused. So this is, kita cakap, okay, kotak ni tak terbang. From the free body diagram, we know that our box is not flying. Therefore, net in the Fy is equal to 0. What is in our axis? What is in our y-axis? It is r minus mg cosine 18. So r is mg cosine 18. Friction is mu r, mu mg cosine 18. And then bila kita nak cari W and C, that is F cosine theta between F and S. This is angle between vectors. Bukan angle kat sini dah. Angle lain dah. Angle between vectors. So F theta between S. So F is this way. We know that F is always this way and our S is the other way. They are opposite direction. Therefore, it is a cosine 180. This is equal to -1. Okay, so this is how I got the cosine 18. Faham ke kenapa cosine 18?
Faham.
Faham dah? Okay.
Dah faham.
Okay, sekejap saya nak kena berehatkan tekak saya sebab saya sakit tekak. So bagi saya 4 minutes, 3:20 Sebab tadi pun saya ada kelas 2 jam kak. So, waktu saya macam petang-petang saya celaluk sikit. Kenapa Soh menangis? Okay, cosine 18 because of R. Okay, betul Feli. And the -1 thing from cosine 180. Yes, correct. So Adam, saya menjawab soalan awak. So hopefully that is okay for everyone. Kalau ada soalan lagi, please ask. Do not worry. Okay, after this example, we have kita dah buat yang ni. Is this the same one? No, this is 4.6. Okay. Excuse me, sorry. Okay, I think it's time. Okay, thank you for giving me that break. I needed it. Okay, so kita akan sambung with power. Power is not something, I haven't told you guys about power yet, but it's very much related to work done. So power is equal to work done divided by time, or the change in energy over time. So whenever you have a change in energy and you divide it by time, you will get power, and the unit is watts. The unit is watt, ataupun you can say 10W, capital W, capital W is watt. So ataupun you can say it's joules per second. It would mean the same thing, just like joules is equal to Newton meter, and if Newton is equal to kilogram meter per second squared. So watt is also equal to joules per second. So dia ada, this is the SI unit lah, but you can also use this unit. If it helps you to remember better, you can use it. Okay, so that is your definition for power. Is pretty easy, nothing to, tak ada benda yang tricky lah about it. So let's do this equation. Kat sini ada cerita pasal power, the work done per second. So a block of weight 120 Newton is moving downwards. So it's moving downwards, this is our motion. I don't want to put it inside my FPD. So this is my motion. And it is downwards along a plane inclined at an angle of 30 degrees with the horizontal. So it's saying that this incline is 30 degrees at a constant speed of 10 meter per second in 3 seconds. So what do we know about constant speed? What do we know about constant speed? What are the conditions for constant speed? So Feli and Elisa is saying A equals to 0. Haikal cakap kosong. Kosong apa? Naziha saying no acceleration. Yes, correct. So when you have your V ataupun U is equal to V, it means that your A is also equal to 0. What is another thing associated with acceleration equals to 0? What is another thing associated to A equals to 0? In terms of equilibrium ke tak ke? In rest, F net equals to 0. Yes, correct, Ian. That's the right answer that I'm looking for. F net is equal to 0 when your acceleration is 0. So in this case, particularly in our motion punya axis, our imaginary axis over here, we know that this guy punya fx is going to be equal to 0. What about our fy? Is it equal to 0 or not? Is it flying?
No.
No. Therefore, the net in the fy is also equal to 0. Okay. Okay, so everyone is okay. Betul. So thank you everyone for trying. It means you remember that what we learned in chapter 3 lah. So here we know that our net in the fx should be equal to 0 in our imaginary axis over here ataupun our x-axis over here. So we want to know what is our friction, because we want to know what is the work done per second in overcoming friction. So basically what this question wants is asking us to find the work by non-conservative force, or in this case, friction dot with S. They want us to find the work done to overcome friction, and then they want us to find out what is work over time so that we can know what is the power. So this is what the question is asking. So now our job is to find out what is friction. So let's draw our free body diagram. Okay, so this is my mg. Skip. This is your angle, and this is your mg sine theta. This is mg cosine theta, and this is your r, and this should be your friction. First of all, make sure our free body diagram is correct, and then use your condition. So from this condition, we know that whatever that is in our x-axis goes into our equation. So 0 equals to mg sine theta. We are assuming positive side on the right hand side. So mg sine theta minus friction. Therefore, we know that friction is equal to mg sine theta. I'm just bringing friction over here. So friction is mg sine theta. Since I know what is mg, it is 120 Newton, and I know what is the angle. So this is 120 times with sine of 30. So that would give me friction as 60. Okay, 60 Newton. So that is your friction. So now our next job is to find out what is the work done. Banyak lagi kerja ni, baru jumpa friction sahaja. Okay, so moving down here and then move this away. So work done by non-conservative force in this case is our friction and our S. Our S is this way and our friction is this way. Now immediately looking at this, our two vectors F and S are in the opposite direction. So I can say that, okay, they are parallel and they are in opposite direction. I can say that they are negative work. So friction is 60 and S is, we don't know yet what is S. Or I can say that 60 cosine 180 times with S. I can also write it like this. Dua-dua betul, tak ada masalah. How did I get the cosine 180? We talked about this earlier. So F is in the opposite direction with S. The angle between them is 180 degrees. This is the equation for work done. The basic equation for work done. This is the angle between the two vectors. Saya suka letak dekat tengah-tengah ni because it reminds me that this is the angle between the two vectors. This is why I put it in the middle instead of hujung. Okay, so we don't know what is S, but we know that we have a constant speed in 3 seconds. Can I find out what is my S or what is my displacement? Do I need to use my linear kinematics? What should I do? So S is equal to... So if I'm going to use my linear kinematics, I'm going to use equation apa can I use V squared equals to U squared plus 2AS or not? So V squared equals to U squared plus 2AS. If I'm going to use this equation, my A is 0 because constant speed equals to A equals to 0. So this gives me V equals to U. Doesn't really help me to find S. What equation should I use? 1 over 2 U plus V T. So S equals to, okay, let's try Feli's approach. So Feli is saying S equals to 1 over 2 U plus V times T. And we know that U is equal to V because they have a constant speed. So this is 10 plus 10. And this is 3. Boleh. So I can solve for S. So this is 20. 20 divided by 2 is 10. So I get 30 meter. So I can plug it inside my equation. This is going to be 30. So my non-conservative work done is equal to 60 times cosine 180 times 30. So that is 1,800 joules with a minus sign. So that is my non-conservative work done. And then it's asking what is the work done per second. So this is done in 3 seconds. This is the work done in 3 seconds. It's asking us what is done in 1 second. So cari je lah macam biasa. So work done is over time. So you would get 1,800 divided by 3. So you would get 600 watt. You need to include the negative sign, you can. Boleh juga. Tak kisah. So minus 600 watt. So let's see. Yes. So kat sini dia tak letak the negative sign. How do I explain this? Kat sini dia tak letak negative sign because they already know that we are referring to the non-conservative work done. Sekejap, If use 10 equals to ds over dt, boleh ke tak, doktor? So you want to integrate lah. Naziha wants to integrate. My God, boleh. Boleh. ds dt, betul. So Naziha is saying, can we use 10 equals to ds dt ataupun the change in s over the change in t, where the change in t is 3. Kan? Nak nangis juga ni je, tak adalah. So yes, you can. Mathematically, it should comply lah. Okay. So physics dengan math ni dia macam kawan baik lah sebenarnya. Walaupun saya tak suka math tapi terpaksa juga. So boleh. So this is what you get, 1,800. Sepatutnya negatif lah sebab non-conservative work done negatif. And then power is divided by 3. All right, so next question. This is the last one from our PBL, from our module. And then kita akan go for our textbook punya examples because I believe like chapter 4 needs a lot of explanation. Kita akan go for that as well later on. So let's do the last one from our textbook. How much power is delivered to a turbine below a dam of height 50 meter? Okay, so ada turbine. This is our turbine. Turbine below a dam. So this is our dam. Dam kita kat sini. From a height of 50 meters. So it's saying that the distance between the dam, from the top height of the dam to the turbine, this guy is equal to 50 meter. 50 meter. So the height difference between them is 50 meter. So they didn't specifically say, oh, the dam is 50 meter and the turbine is h equals to 0. Tak, they didn't say that. They're just saying that the distance between the dam and the turbine is 50 meter. It doesn't care where is 0, where you want to say 0. Tak kisah. So if you want to put h equals to 0 over here, this guy will become h equals to minus 50. But why would you want your life to be difficult? So you just put your bawah ni as 0 lah. So 0, 50. Ataupun you can put this is 0 and this is h equals to minus 50. Asalkan the distance between them is 50. You are good to go. So the distance between them is 50 and it delivers 1 meter cube of water in 1 minute. So time is 1 minute or 60 seconds. Okay, and then it delivers 1 meter cube. And we can find out what is the mass using rho times volume. So mass of the water is rho times volume. Ini rho tak tahu kenapa letak R. Rho is 1,000 kilogram per meter cube times with 1 meter cube. Cancel out. So you get your mass as 1,000 kilogram. So now we can find out what is our energy. When this water over here goes down to the turbine, what is it experiencing? Anyone wants to guess? When it goes from here down to the turbine, what does it experience? Come on guys, this is like easy. We have a change in the vertical displacement. Hint. Semua dah macam mengantuk agaknya. Come on guys, what is going on when we have a change in vertical displacement? Apa dia?
MGH.
We have a change in MGH, that is correct. So when I started from the top and I go down here ataupun over to the turbine, I have a change in H from 50 to 0. So there is a change in our UG. Change in UG. So I started with 50 and then this becomes 0. Okay, so where does the energy go? Where does it go? Oh, tapi korang tak familiar dengan turbine kot? Ke dah familiar? Saya pun tak tahu apa yang korang belajar kat high school. KE, yes, Feli saying that the energy is going to be converted into kinetic energy that is going to rotate the turbine. When we rotate the turbine, it generates electricity. This is where we get our green energy from water ataupun hydroelectricity. The water has potential energy. This water then goes down, and as it goes down, it is losing energy in the form of speed. Bila dia turun, dia akan jadi laju kan? Dia turun, dia laju, it is gaining speed. That speed is when it enters this turbine, that speed dia gerakkan turbine tu. The water yang laju tu, from the UG it became KE, and that KE pushes the turbine ataupun rotates the turbine, and this guy when it rotates, it will generate the electricity. Kita tak belajar lagi macam mana dia generate kat sini, tapi kita tahu that there is energy coming from the water because of the height difference. and then convert it into KE to rotate the turbine. Nanti kita belajar pasal yang atas ni pula, macam mana nak jadi electricity. But right now kita tak belajar lagi. So it rotates and therefore there is a change in energy, and this is going to be our change. This is going to be our work done. So if I wanted to know what is power, I need to know work done over time. So here M is 1000, and then this is 9.81, and this is 50. This guy is 0 divided by 60 seconds. Whatever that is, you will get your answer in watt. So let's see the answer. So 1 times 1000 times 9.81 times 50, this is the answer. And power delivered in 1 second is work done, same answer over here. Kenapa dia buat macam ni? So 1, 2, 3, 490.5 times 10 to the 3 divided by 60. So you would get 8175 watt or 8.175 kilowatt. Dua-dua boleh, sama je jawapan dia. So 8175 watt. Malas nak kira pakai calculator. 8175 watt. Okay, so faham So we didn't have to do EI equals to EF because we knew that the energy was converted to become kinetic energy. We just wanted to know what was the work, what was the change, what was that change. So this is the change, and that is enough to answer a power punya soalan. Sebab power ni senang juga. Okay, so moving on to this one. Kita dah start lagi dengan spring punya example. So kita fokus on MGH and KE dulu. So wax your skis. Example 5.4, this is page 131. If you're wondering where is this ebook located, it is in your web assign. Tekan ebook. You will get your ebook there. Siapa yang belum pernah buka ebook lah I believe a lot of you have used the ebook, so that is good. Okay, so the problem here is a 60 kilogram skier is at the top of a slope. So she is here. Is it a she? No. Oh yeah, it's a she. So she is on the top of the slope as shown in this figure. At the initial point of point A, she is 10 meter vertically above point B. So they are saying that this is 10 meter above point B. Setting the zero level for gravitational potential energy at B, setting the zero level at B. What that means is that this is going to be your H equals to 0. This is your reference point. Therefore, if this is H equals to 0, this would be H equals to 10. Okay. Find the gravitational potential energy for this system when the skier is at A and then at B. So it's asking for UG at A and then UG at point B. Ini at tulisan saya buruk. Kita buanglah at ni. Okay. So this is UG at A and then this is UG at B. Dia nak tahu apa. And then find the change in potential energy as it goes from point A to point B. And then it's asking us for change in UG, where this is going to be UGB because this is final minus UGA. So this is part A. So let's do that. So UGA senang je MGH. What is H? This is 10. This is 60 times 9.81 times with berapa tadi? 10. Jangan tidur jangan tidur. I'm still awake, so you guys should be awake as well. So this is 60, 9.81, and this is 0. So the difference between UGA and UGB is 0. Whoops. Sikit lagi. 0 minus penat kan petang-petang buat calculation. So 60 times 9.81 times with 10. So you would get this as my 5886. This is 0. So 0 minus 5886 is equal to minus 5886. So that is for A. And then B, soalan B pula. Mana B? This is A. This B. Repeat this problem. Let me use a highlighter. Sumpah tak nampak. Repeat this problem with zero level at point A. So sekarang dia cakap okay tak nak letak H as zero, tak nak letak B as H zero. Dia cakap dia nak letak sini juga. Saya suka tikau lah, letak je lah. So H equals to 0 ke atas pula. H equals to 0 at point A. Repeat this problem with zero level at point A. So if our point A is 0, our point B needs to be minus 10. Sebab dia kena ada difference of 10. Okay. So it's asking us repeat this problem. Cari UGA, cari UGB, cari change in UG. Okay. So let's do that. So what will happen? That is the question. So group, make this smaller. You go over there. Tekan pula. Silap. Okay. Dude, stay still. Kan dah hilang. Okay, I'm putting it here for our reference. And what happened to our H? Alamak, send to back. This is our new B. Okay. Okay, boleh lah tu. Okay, so continuing with our part B. This is part A. Where H dekat atas equals to 10, bawah kosong. Now atas kosong, bawah minus 10. What happens? So UG at point A, don't use at, okay, this one. So MGH at A, this is 60 times 9.81 and this is going to be 0. 0 kat UGA. And then UGB, this is MGH as well. So 60 and our H at point B is minus 10. Minus 10. So this would give me minus 5886. And the change in UG, so UGB minus UGA, I would get minus 5886 joules as well. So this is the same as over here. What does this tell us? It tells us that gravitational potential energy ni sebenarnya is a relative energy. It's a relative energy. When we say U equals to mg, we are assuming that we are referring to the ground level, which is always 0. This is our assumption. This is how we get U equals to mgh. We are ignoring the mg times 0, which is the ground level. But in reality, U is always a relative energy because whenever you change the H, macam mana pun tukar H value dia, jawapan dia akan tetap sama asalkan the difference is the same. So UG is a relative energy. I want you guys to understand that your H reference can be anywhere. Your 0 can be anywhere, but the difference between the 2 points must be the same. Okay, so let's say your H over here is not 0, but it is a 5. So this guy needs to be minus 5. So where is your 0 actually? Your 0 is midway over here. So boleh ke? Boleh, because when we're talking about the change in UG, we don't really care about the H values. But H ni adalah assumption kita. H ni is something that we make it ourselves to make our life easier. And to make our life easier, kita cakap ground level is 0 untuk bagi hidup kita senang. But in reality, it can be anything. So sometimes problem akan trick you guys like this. They can say, this is ground level, and then akan ada air. Air ni adalah minus 5 meter down here. So dia tanya, the reference point is below the water. Macam mana? So kat sini jadi H kosong. So the reference point depends on the problem, but most of the time we assume that our ground level is H equals to 0. But in reality, this energy is a relative energy. As long as the distance between the final and initial is the same, you will get the answer. Okay, so next one. C, repeat again with 0 level 2 meter higher than B. So now instead of H equals to 0 down there, which is what we like, it's saying 2 meter above B is H equals to 0. Mengada-ngada, tapi betul lah, boleh je. Minus 2, so this becomes H equals to 8. What would happen to our equation? Buat lagi. So this is A akan jadi 8 and B akan jadi minus 2. So what would I get? And what would I get as the answer? 60 times with 9.81 times with 8. So I would get this as 4708.8. 60 times 9.81 times with minus 2. I would get this as minus 1177.2. And then UG is UGB minus UGA, so that is going to be minus 1177.2 minus 4708.8. So the answer is the same, 5886. Sama This again shows you that MGH is a relative energy. Asalkan tahu distance between final and initial, your answer will always be the same. It doesn't matter where your reference point, where your H equals to 0 is. Okay, so I hope everyone is okay with that example. That example is in your textbook. You can go look at it. Kan sama, jawapan semua sama. Minus 588. Okay, do we have time? We have time. I'm tired already. Okay, sikit lagi. Satu lagi example. So platform diver. So a diver of mass m drops from a board 10 meter above the water's surface. So kat sini our water surface is now our H equals to 0. And then this is our H equals to 10. A diver of mass m drops from 10 meter above the water, neglect air resistance. Yay. So EI equals to EF, tak ada W and C. Use conservation of mechanical energy. So EI equals to EF, no W and C. To find his speed 5 meter above the water's surface. Above kat sini. Dia suruh cari dekat H equals to 5. So how do we do this? And then it's asking us for V over here, and then V, find his speed as he hits the water. So V dekat sini juga. So this is for question number B, and this is question A, and this is question B. So let's do it, laju-laju. So EI, expand this equation, we have KE initial plus UG initial equals to KE final. Sikit lagi korang, please focus this over here, nanti susah nak jawab nanti. So KE final plus UG final. So we know that we started with 0, V equals to 0 because the diver did not start yet. So kita akan cakap, okay, mula-mula KE dia kosong. Tapi dia ada potential energy sebab dia dekat atas. So M is M, and then this is G, and then H is 10. So this is our UGI. And then for KE final, we will say that this is our final point for part A. This is our final point because we want to know what is the V over here. Final for part A. So 1 over 2 MV final squared plus with, at this point, your energy is converted into KE and also UG. So 1 over 2 MV final squared and MG5. Now remember, previously we talked about MGH yang converted terus jadi KE bila sampai dekat hujung. Tapi memandangkan this guy tak sampai hujung lagi, dia baru tengah-tengah. So this energy is converted into both KE, it loses UG, dia akan berkurang dia punya UG ni, tapi dia punya KE akan meningkat, dia akan increase. So this is what is going on. We started with mg times 10. This energy is transformed into Ke, part of it, and part of it is retained as Ug sebab dia masih dekat tengah-tengah udara, ada potential energy. So with that said, we can try to solve this. So mg 10 minus 5, this is 1/2 mv final squared. M cancels out, and then you can solve for v final, which is, if I use my calculator, I will get 9.9. Okay, so now for part B, this is part A. So for part B, the final is now over here. We want to know what is the V over here, so we need to assume that this is our final energy punya tempat. So EI equals to EF, and EI is the same. So 0 plus mg10, sama macam tadi cuma E final je yang tukar. So sekarang ni we have 1/2 mv final squared plus with mg times 0. mg times 0. So previously our mg10 was converted into Ke and Ug. Now this guy is 0. Our Ug is transformed completely into Ke. So senanglah hidup kita. So M cancels out. So 9.81 times 10. And then divide, times 2. Divided, square root of that. I would get my V final as 14 meter per second. So what does that mean? When the diver is from here, his velocity is 0. When he reaches this part, his velocity is 9.9. When he reaches the surface of the water, his velocity is 14 meter per second. So dia punya Ug is converted into Ke, lagi dia converted into Ke lah. Mula-mula separuh ni dia converted into Ug and also Ke. Kat sini where his potential energy dah habis, semua jadi Ke, sebab tu Ke kita lagi besar dekat sini. Okay, habis dah. Saya pun dah tak larat. Okay, take care guys. I think that is it for today. We will continue with our spring examples in next class. Alright? Dah tertidur dah semua orang. Bye guys.
Thank you, Doktor.
Welcome.
Thank you, Doctor.
Thank you, Doktor.
Thank you, Doctor.
Welcome.
Oh, Doctor, sorry.
Hi Jana. Sorry. Okay. Kenapa sorry? Kenapa sorry?
Tak interrupt, Doctor.
Oh, okay.
Tak, itu eksperimen punya result.
Oh yes, betul. I wanted to talk about that too. Mana saya punya phone kejap
Doktor.
Okay, so as tanya pasal eksperimen, I think Ian pun tanya juga. Kejap Let me go back to your question. So here, so cakap, is it possible for the value of E losses to be 50 and then kejap 33, kejap kosong, kejap ni. Loss dia agak banyak Kejap. Let me see. Yes. Yang lain ni nak dengar ke dah tertidur? Experiment 4. So experiment 4. Boleh ke loss dia 50? Sebenarnya boleh. Cuma yang saya rasa pelik would be if your loss was 90%. Tu salah. Bagi saya tu macam you have to repeat the experiment lah. Kejap let me see your calculation kejap. So H is, let me open your time. Am I still sharing my slide or tak? Okay. So this is free. Lepas ni tak ada apa-apa dah kan, so?
Tidak ada, ini saja.
Okay, sekejap saya tengok balik saya punya skema jawapan. If it is sama dengan solve ke tak. Approximately lah. Okay. Documents. Experiment 4. Okay, so premium is equals to, so your height is 0.76, 0.66, 0.56. Okay, so ada pengurangan by 10, and then your R is measured. Soalan mana? Kejap, so kenapa awak tak isi table yang dalam worksheet
Oh, sebab saya tulis dekat itu paper tu baru fill in dalam itu dokumen. Yeah.
So your V is found from equation 4.3. Equation 4.3 is, excuse me. Equation 4.3. So V equals to R over T. Okay, betul. R is 1.06 divided by time. Your time is 0.38. Should be betul lah, 1.06 divided by 0.38. Okay, yang first dah betul, 2.79. And then your EI is MGH. EI adalah MGH, betul. Your EI is MGH. Your E final is, okay, that's to your loss. You kira loss macam, oh yelah betul lah, MGH tu lah 1/2 MB squared. So 0.04 dot M is 0.05 milligram is 5 gram is 0.005 betul, times 9.81 times with capital H. Capital H 0.76. So you get 0.03, 0.04. Oh, okay, buat 2 decimal place terus. And then for your 1/2 MB squared, kalau kita buat 0.005 times 9.81 times with 0.76 and then terus pakai macam ni tolak dengan 1/2, so 1/2 times with M 0.005 times with your V is 2.79 times with your V is 1.06 divided by 0.38 and then square that is your V and then divided by E initial 5 times 9.81 times with 0.76 times with 100. Okay. Kejap dapat kosong kejap dapat 50. Kenapa Well, this is actually normal untuk dapat errors, but if I notice that if you use the values without rounding them off, contohnya kat sini so cakap your EI is 0.04 when it could be 0.037. So when you use your values as it is instead of 2 decimal places, you would get better accuracy lah. So what I calculated for you is Your E loss untuk yang first line tu, instead of 50, I got 47%. So if you want to have a more accurate answer, that is one way to do it. Use the values, jangan round off. Or you can just use it as it is, dapat 50 ni, and then discuss kenapa error tinggi. Boleh jawab je so, asalkan jalan kira betul.
Then kalau sebab kalau guna 0.037, this means like all of the data we have to have the yang serangkam, itu perpuluhan yang serangkam kan?
Betul. So my suggestion is just keep it as it is lah, and just discuss kenapa error tinggi.
So if discuss, I would like to say is because of the digit problem or
Apa? Digit?
like the error will affect this.
Oh yes, you can see the round off error juga, boleh include that, and also because your system kadang-kadang bola tu tak sentuh all points of the incline, that could happen as well. Ada tak?
Okay.
Dia bounce off instead of dia glide, so that could happen as well. So benda-benda macam tu lah you have to discuss. Okay, so?
Yeah, I understand, Doctor.
Alright. Anything else?
I think that's all.
Okay, bye. Take care.
Thank you.